At our lecture 5 today. So today is will be our lecture 5. Right. In the last session, we had discussed about we had just began our discussion on space curves. So as we recall that the curves in general tend to lie in, of course, in the 3D Euclidean space. And plane curves happens to be a special case of space curves, and we saw certain examples of plane curves in real life scenarios. And what we concluded is that the plane curve can be obtained, determined to the point of isometry by the curvature function kappa of S. Right. However, for a space curve, it cannot be. We cannot just define it using the curvature function only. We require one more function, one more smooth function that we call as the torsion function. And by a combination of both, using both curvature and torsion, we can define a space curve uniquely. Of course, we exclude that you can have multiple curves which are just isometry which are asymmetric to each other, right? So we began with a unit speed curve, defined all these evolution equations that we later called it as the Frenes-Array equations, which are the equations for t dot, I mean, the tangent vector, the normal vector, and the binormal vector, which are respectively t, n, and b vectors, right? So these equations are called Frenes-Array equations, and they form what is called as a Frenes-Array frame. Right. So so this is what we talked about, and then we also derived the equations for what if the curve is just happens to be a regular curve and not with such special features, such what we call as the unit speed curve, right? So yeah, we were able to get those expressions, and finally we ended up with deriving an expression for kappa of a general regular curve, and also for the torsion function for a general regular curve. So today we'll start off with some of the definitions and propositions, of course. So let's start with. So I'll be switching between two books. So for certain things, I'll be using Presley, and for others, I'll be using Bankoff, right? The book by Bankoff and Lovett. So let's have some propositions and definitions. So the proposition goes that it says that let gamma vector be a regular curve. In R3 with nowhere vanishing curvature. Right? So that the torsion tau of the gamma vector is defined, of the curve gamma dot is defined. And as we recall, the torsion depends on curvature, and curvature happens to be the denominator in the expression, so to speak, right? So you see in this expression here, this forms the numerator of the curvature. And so which means if we need the curvature to be non-zero, then only the denominator of tau t is going to be non-zero, right? So it's defined. Then the image of gamma vector is contained in a plane if and only if tau vector, tau is 0 at every point of the curve. Right, so this is what we had. So let me read it. Let's read it again. So let gamma vector be a regular curve in R3 with no vanishing curvature. Then the image of gamma vector is contained in a plane if and only if tau is 0 at every point of the curve. Right. So maybe we'll have a small proof. Of course, we'll try to avoid proofs since we have a lot to cover and we are not, and our aim is to understand the concepts of differential geometry without going very much into proofs. So let's say that gamma vector is unit curve or a unit speed curve. And of course, we recall that we can anyway reparameterize any other curve in a unit speed curve, right, as a unit speed curve. Then say that gamma vector is contained, or the image, so to speak, the image of gamma vector is contained in the plane v vector dot n vector is equal to d. And as we recall, this is the equation of a plane that we have learned in class 12 years in the right. So v vector is is an element of R3 and it lies in the plane. N vector is normal to the plane. And d is some constant, is a constant. And it's, of course, it's a scalar. Okay? Now, and let's assume that n vector is a unit vector. So we can, and v vector we can just put v vector can be gamma as well, since curve is lying in the plane. So gamma this is equal to d, and let's say differentiate with respect to s, right? So usually let me call it gamma of s is a unit speed curve, so that it's implied that s is the arc length parameter. Then this gives us gamma prime or gamma dot, that's what we have been following, into n plus gamma s dot n prime, or sorry, n dot is equal to 0, since t is a scalar. And then we recall that even n vector is a constant vector. So this implies that this is also equal to 0 vector. So eventually you have gamma dot s is dot n is equal to 0. And then gamma vector is t of s dot n is equal to 0. And if let's differentiate it again. Then we have t dot s dot n vector is equal to 0. And we recall that t dot s is kappa s and s, right? Kappa s and s, right? Dot n vector is equal to 0. So since kappa, since kappa of s is not equal to 0, because that's then only we can properly define tau, right, is not equal to 0. So this implies that ns vector dot n vector is equal to 0. So what we see that both, this implies that from this we conclude that this statement as this, that t vector and s vector and n vector are both perpendicular to capital N vector. Right. So this implies that t vector cross n vector is equal to b vector. This is going to be parallel to n vector. Right. So this implies that we can either have b vector is equal to n vector, of course b as a function of s, and anyway it's going to invariant of the best s, right? And or perhaps b vector of s is equal to minus n vector. This is for all s. Either of the two we can have. Right. So this implies that b vector of s is equal to 0. Right. The b vector dot is going to be 0. And this implies that we recall that b of vector of s is equal to tau of s into n of s. Right. That is that from the Frenet equations. That's what we had, right? Okay, minus tau s and ns, right? So you have minus tau s and s. Now, since this is equal to 0, and of course, n vector is not equal to 0. So this implies that tau vector of s is equal to 0. Right? So this means that there is no torsion. And then, and since the curve is lying in the plane, the torsion is 0. Now let's go the converse. So conversely, so we want to prove that, say if tau of s happens to be 0 throughout, then the curve has to lie in the plane. So we start with, say, tau of s is equal to 0 everywhere. Then b vector is equal to minus tau s n vector is going to be 0. So this implies that b vector of s is constant. Right? So since we know, and for a curve to lie in the, so for a curve gamma to lie in the plane, what we are required to have is that gamma vector dot n vector has to be equal to some d vector. Again, or in this case, say in general, v vector dot b vector, right? B vector is anyway constant. So say b vector happens to be the normal to a plane, then v dot b is equal to constant for v vector is an element of R. Now, then say, then even the curve, say let the curve lie in this plane. So then gamma dot b vector is equal to constant. Then this implies that, say we are differentiate with respect to s, gamma vector dot b vector is equal to 0. And this is going to be gamma dot b vector is equal to 0. And of course, the thing remains that b dot vector is going to be 0 vector anyway. So then this implies that t vector dot b vector is equal to 0. So which means that the tangent vector is perpendicular to b vector, which we already know. And so okay, so here what I have, let me just little correct this. we are not assuming anything. Say right now, we just say that, okay, we have gamma dot b is equal to 0 and then all this. And what we later learned that so this implies that is equal to 0. So here we recall that from here we can deduce that t vector is perpendicular to b vector, isn't it? So, and gamma dot b vector is equal to constant. So we have gamma dot b is equal to constant and v dot b is equal to constant. When both happens to be, so it implies that gamma vector is indeed contained in the plane, say v dot b vector is equal to t. So this was going to so we are able to complete the second part of the proof that v dot b is equal to d. And which means that if tau is 0 everywhere, then it implies that the gamma is a planar curve and it lies in a plane gamma dot is equal to t. Okay, so what we had discussed yesterday can be put in terms of a theorem. It says that let gamma vector be a unit speed curve in R3 with nowhere vanishing curvature. Then, of course, t vector is equal to kappa n vector, n dot vector is equal to minus kappa t vector plus tau v vector. Then b vector is equal to minus tau n vector. So these equations, as we recall, they are known as Frenet-Serre equations. And we also know that they can be mapped as if t dot n dot v dot 0 kappa 0 minus kappa 0 tau 0 minus tau 0, and then we'll have t and b. So this matrix here is skew-symmetric matrix, and we clearly see even from its structure that say if this matrix is A, then A transpose is equal to minus A, right? So in A transpose, this will go here, and when we compare, it is as if we are having this element to the minus of the transform matrix, right? So that's what it is. And a few more theorem. One more. Let me have one small proposition here. So it says that, of course, we are not going to prove it, and although it's very straightforward. Let gamma vector be a unit speed curve in R3 with constant curvature and zero torsion. then gamma vector is a parametrization of or either part of the circle. So from the question, what we say is that from the proposition that if gamma vector is a unit speed curve in R3 with constant curvature and zero torsion, then gamma vector is a parameterization of part of a circle. Yeah, let's just little discuss here, of course. Yeah. So given that kappa of S is constant and tau of S is zero, there is no torsion anywhere. So kappa of S is constant, so we can just call it simply as represent it just by kappa without without any argument to it. So what we see from the Freynes array equations is that T vector is equal to kappa n vector. And let me also take proper arguments. And n dot vector of S is going to be equal to minus kappa T vector of S. And of course, 0 into P. So anyway, this term goes away. And then B vector of S is equal to 0 vector. Right? So this implies that B vector is constant. Now from these two expressions here, from these two expressions, what we know is that right. So what we know from this text, I mean, we look at, so this is given by d gamma by ds is equal to kappa of n vector s. It's going to be from here n vector of s is going to be minus kappa d gamma vector by ds. Right. So this got the upon expanding, this is what we have. Now we consider this too. So what we can do in this case is that I mean, Just take a look at this expression here. This can be written in this following manner. And we can write it down as d by ds of gamma vector kappa plus n vector is equal to 0. So this implies that gamma vector kappa plus n vector is equal to some constant, right? Some constant vector. Then this implies that gamma vector gamma vector minus or gamma vector plus n vector by kappa is equal to a vector by kappa. Since kappa is constant, this is what we can do. So this a vector by kappa vector, we can write it as b vector since kappa is a constant and a vector is also a constant vector. So this implies that gamma vector minus b vector is equal to minus n vector by kappa. So far, so good. Now take the norm. Take norm on both sides. We have gamma vector minus b vector. Norm is equal to minus norm of minus n vector by kappa. And this is going to be equal to, and n vector is a unit norm, right? So it's anyway one, it's the norm of n vector is 1. All we have is 1 by kappa. And so what we see is we clearly see that if say b vector is some center, is some point, right? In this 3D frame, in 3D Euclidean vector, I mean this space, and then gamma vector is say here, then the norm of gamma minus v just gives us the distance of between the points gamma vector and p vector, and any gamma vector which, so it seems that we are looking for all those gamma, and since gamma can be any element in R3, but which lies on the curve, of course, and this distance always has to be 1 by kappa. So it's as if you're always looking this gamma, the equation for this curve is given by any point which lies at a distance of 1 by kappa from b vector. So that is what, that's essentially the equation of a I mean sphere, right? I mean it's as if this curve lies on a sphere. Since 1 by kappa is some sort of a radius, of course it is a radius, so 1 by kappa. So that is what this proposition is trying to say. Likewise, let's talk about one more theorem and then move ahead. So theorem says that let gamma vector of S and gamma vector tilde of S be 2 unit speed curves, be 2 unit in R3 with the same curvature kappa of S is greater than 0, and the same torsion tau of S for all S. Then there is a direct isometry of R3, direct isometry M of R3 such that gamma tilde vector is equal to M of gamma vector of S for all S. Now say further, if K kappa and say if K and T, just some functions, are smooth functions, with K is greater than 0 everywhere, there is a unit split curve in R3 whose curvature is kappa K and whose torsion is T. So yeah, for proof, please refer to theorem 2.3.6 of Presley's book. Right? So now let's switch over to a new topic, what we call as the global properties of curves. So you'll okay. So the first question that comes in mind is, uh, what are these global properties of curves, right? So I must tell you that so far we have been discussing about local properties. So we have been discussing about so far. We have discussed local properties of curves. That is, the properties depend only on the behavior of a curve near a given point. And not the global shape of the curve. So the properties like curvature, torsion, and all those tangent vectors, tangent, normal, binormal, There are all local properties. So in global properties, we often require concepts from topology, but since this is an introductory course in differential geometry, without any expectation of us having been introduced to topology before, we will only be using certain results, so to speak, of from topology rather than going very deep into topology, right? So at first, we start with, right? So we begin with defining what is a closed curve. So we begin with a definition. And this is about what do you mean by closed curve. So say that a parametrized phase curve C is called closed if there exists parametrization gamma vector which maps from A, B, or we'll just use our A, B to R cubed of C such that gamma vector alpha is equal to gamma vector beta. So this is called as a closed curve. Now a closed curve is of class. So this was some subscript, right? So I should just script C indicates curve. So a closed curve is of class CK if, in addition, all the one-sided of course, at some points we'd have one-sided derivatives, right? Of course, those would be the endpoint of of this gamma vector at alpha and beta are of order I is equal to 0, 1 till k. In other words, if as one-sided derivatives gamma vector A alpha is equal to gamma dot beta, likewise gamma double dot alpha, gamma double dot beta, and so on up to gamma vector derivative of order k at alpha is equal to gamma vector of order at beta. Yeah. So these are just to ensure the continuity of certain properties, all the derivatives at these endpoints, which. So now a space curve, same C, is called simple closed curve if it has no self intersections. Okay, sorry. So let's not jump the gun. So space curve C is called simple if it has no self intersections right? Okay, so a space curve C is called simple if it has no self intersections, and a closed curve is called simple if it has no self intersections except the endpoints. So this is a pretty long definition, but yeah, that's how it is. Yeah. So, so, so we first define what we call as the closed curve. If there is such parameterization such that at the ends, uh, the gamma vector at alpha is the same as gamma vector as beta. Then we talked about what is a simple curve if it has no self-interest. I'm sure we had discussed it some time back as well. And a closed curve is called simple if it has no self-intersections except at the endpoints. Right? So we have a proposition following this. If there is a proposition here, says that if a regular curve is closed, then it is bounded. Right? So we'll not be proving this as of now, and we'll just keep it as it is as a statement. So we had discussed about a simple closed curve, right? Simple closed curve. And it has an equivalent in, of course, the planar curve, it is a special case of this space curve. So anyway, the simple closed curve in R2 will also have an equivalent. So say for R2, so for R2, a simple curve, simple closed curve in R2 is a closed curve in R2 that has no self-intersections. And these are all a special case of, just highlight this in. So it's a standard result of the topology of R. R2. And this called the Jordan curve theorem. And it says that any simple closed curve in the plane has an interior and an exterior. So it's more precisely the complement of the image of gamma vector and as we recall, the complement of the image of gamma vector are the set of points of R2 that are not in the image of gamma vector. So the complement image is the disjoint union of two subsets of R2, and those are denoted by INT, means interior of gamma vector, and exterior of gamma vector. And the properties are that interior of gamma vector is bounded. So that is, it is contained inside a circle of sufficiently large radius. And the property of exterior of gamma vector is that it is unbounded. And third part is that both the regions interior of gamma vector and exterior of gamma vector are connected. That is, they have the property that any 2 points in the same region can be joined by a curve contained entirely in the region. But of course, any curve joining a point of the region and interior of gamma to a point of exterior of gamma must cross the curve gamma vector. So yeah, so there was enough of too much mouthful. So let's try to figuratively explain this, right? So what we have been talking is that this curve, say we have this curve. Let this be gamma vector of alpha and point this side be gamma vector of beta. And they happen to be coinciding. So this is an example of, so it's as if we start from here and then trace along this line. And our S starts from here, right? So maybe make it more. So we start from here and here's a unit speed curve. So which means that where we have this arc length parameter defining everything, defining this curve. So S will be equal to 0 here, and then this is how the S will say increase along the curve. So this is an example of closed curve. And however, what we notice here is that there is a self-intersection. So this is a self-intersection. And say, let's remove this self-intersection, or maybe have a curve in which there is no self-intersection. So say this is our curve. Some general curve. Let's take, just putting it so that we have enough space to define many other properties here. So this is our gamma vector alpha, and this is the same as gamma vector beta. So I could have written it here as well. Likewise, we start from here and just traverse along this line. And this is how this is the increasing direction of the arc length coordinate s. So s is equal to 0 here. And we see that we traverse the entire curve without touching itself again. And we only meet the originating point, which is gamma vector of alpha at alpha. So this is what we call as the simple closed curve. Simple. And this curve is given, of course, as gamma vector of s. Now what we'd say here is, maybe just enlarge it a bit. Towards the images, I will create a better one and slightly larger one. Yeah. So here what we have is this curve, and assume that, of course, we can let's consider this to be R3, R2 in this case, just R2. So we have X and Y coordinates. Some at some arbitrary origin. So what we see that this curve divides the entire R2 into two regions. This is region 1, which is interior to gamma vector, and this is the exterior to gamma vector. Now you see, right? That's what we are talking about. What we say that interior of gamma vector is bounded, which means that it is contained inside a circle of sufficiently large radius. So let's consider a very maybe mildly colored. So and some center it some at this point. So let's start drawing a center here, I mean circle here, centering it somewhere. Draw again, keep on increasing the radius at a time when the entire curve will be enclosed within the circle. Maybe I'm not doing it right. So what we see that this sphere, this circle here, bonds the interior region of the curve. So which means that the interior region is bonded and it's contained within a circle of sufficiently large radius. And this is some radius of R. However, for exterior of gamma vector is unbounded, right? You cannot bound, I mean, you cannot, the area in this case will be infinite. But of course, not exactly infinite, because it has certain region which is excluded. I mean, region which is within interior of gamma vector. So which means that exterior is unbounded and interior is bounded. That's the whole gamut of this, what we're talking about, right? And in the third property, we were talking about that both the regions are connected, which means that if we start, say, any 2 points, say this point and this point, we can just connect by any curve without leaving the region, right? So any 2 points, even this point and this point here, we can just connect it by any curve. And of course, shortest on it with the line which is connecting both, but just as a matter of fact, right? I'm just using curve because we'll see why that's how we have to do in exterior, in the exterior of gamma region. So in exterior gamma, say we have this point here and this point here. This and this. So we need to traverse any path which remains only in exterior of gamma and reach here. So which means that any 2 points can be connected by a curve which joins both without entering into the other region. However, if you want to connect 2 points, one point in interior of gamma and the other in exterior of gamma, then we do need to cross. So like here we had to cross the curve gamma. So that is what the entire story here is, right? Now, just let's take an example. So the example is that, say, the ellipse gamma vector of t is equal to p cosine of t and q sine of t, where p and q are non-zero constants. And is a simple closed curve with period 2 pi. The interior and exterior of gamma vector are given by, right? So interior of gamma vector will be equal to all those points xy is an element of R2 such that x squared by p squared plus, so p and q are the semi-axis of the ellipse. Sorry. Y squared by q squared is equal to, it's of course not equal to, but it will be less than 1. So this is the interior. And the exterior of gamma vector is equal to x of y is an element of R2 such that plus y vector by q square, y squared by q squared is greater than 1. And the image of gamma vector, which is all the points that form gamma vector, is, or which form the curve, right, which it's parameterized by gamma, is xy is an element of R2 such that x squared by p squared plus y squared by q squared is equal to 1. So what we clearly see that this is the region contained within the ellipse. This is the region outside of the ellipse, and this is the set of points which are on the ellipse, right? So there is, of course, which is, it's anyway a trivial thing, but yeah, interior of gamma vector union, or maybe let's start with interior gamma vector and exterior gamma vector is, there are no points which are common to both. So this is empty set phi. Likewise, these are for all they are all mutually disjoint sets. So exterior of gamma vector with the image of gamma vector is also equal to phi. There is no points of intersection. And then interior of gamma vector um, with image of gamma vector is also phi. So this means that interior of gamma vector, exterior of gamma vector, and system. Okay, so interior of gamma, exterior of gamma, and image of gamma vector are all disjoint sets. Okay. Okay. So with this, let me add a few more theorems, and we will do some mathematical what do you call computations today. So there is a theorem which is called Hopf's uh, love says. So it says that the total signed curvature of a simple closed curve in R2 is plus minus 2 pi. And we had recalled that from a previous session that the total sign of any closed curve in R2 is an integer multiple of 2 pi. And if it is a simple closed curve, then it's we just need it's the integer has to be plus minus 1. That's the thing, right? So essentially, the point is that the total signed curvature of a closed is an integral multiple, an integer multiple of 2 pi. Right? And so the point and the aim of Hopf's theorem is that if the curve in R2 if the curve happens to be simple closed, then this, then the integer must be plus minus 1. So that's what it is, right? Okay, and let's add two more theorems to our bucket today. So one is what we call as the isoparametric inequality. But before that, let's build up on what we call as what is the area of a area contained by a simple closed curve in closed curve gamma vector in R2. And this is given by A, the script A, maybe I'll just call it A, which is area bounded by this simple closed curve is equal to, so the the interior of gamma vector into dx dy. But to compute this, we require Green's theorem. So what we'll see is that computing it of A gamma requires Green's theorem, right? Now, what does Green's theorem say? So Green's theorem it says that let f of xy and g of xy be smooth functions. That is, functions with continuous partial derivatives of all orders. And say, let gamma vector be a positively oriented simple closed curve. Right, positively oriented had to deal with the choice of normal vector, right? If it is taken to be pi by 2 anti-clockwise with respect to gamma vector, with the respect to the local tangent vector of gamma vector S at S, then that is called as that it is a positively oriented simple closed curve, right? Okay. So then what we have is interior of gamma vector, right? That is the domain of integration, and then partial g by partial x minus partial over partial y dx dy is equal to gamma vector f of xy dx plus gxy dy. Right? And this is what we often call as the Green's theorem in multivariate calculus. Now the proposition is that, so we have a proposition here. If gamma vector t is equal to x of t, y by t, y of t, and it's a positively oriented simple closed curve in R2 with period t, then a vector of gamma vector, a of gamma vector is equal to half from 0 to t, where t is the period, and xy dot minus yx dot dt. And this can be proved by taking, say, let's just look at the form here, right? So we have dx. So dx is nothing but x dot into dt, right? So x dot dt is equal to dx. Likewise, y dot dt is equal to dy. So let's try to, so this can be written as 0 to t and then minus y by 2, say dx. Let me just call it as the interior of gamma vector. Or not this, let's call it 0 to t. Let's keep as it is as of now. And this one will be x by 2 dy, right? So when we look at the expressions, so therefore what we have is f of xy is equal to minus y by 2, and likewise g of xy is equal to x by 2. And from there, that's how we have this formula here. Right. Now that now we've finally come to what we had tried to set, build blocks, build things up. So we have this theorem, and it is on isoperimetric inequality. Right? So let gamma vector be a simple closed curve, and let L of gamma vector be its length. And let A gamma vector be the area contained by it. Right? Then what we have is, and mind you, we are all talking about, we are still talking about planar curves, right? Uh, so all curves in this is also valid only for, so closed curves in R2. So we don't have, of course, we cannot define what is a generic circle, right? We cannot have any, so to speak, a generic curve, closed curve, simple closed curve, which defines some sort of an area um, in 3D, right? In general, like, if we talk about what is the area bounded by a simple closed curve in R3. So then what we have here is that A of gamma vector is equal to, or sorry, is less or equal to 1 by 4 pi length of the total length of gamma whole squared, and the equality or maybe an equality holds if and only if gamma vector is a circle. And that we know very well, right? We can even look at for the if and only if part, what we have is L of gamma vector for a circle, gamma vector of radius r is 2 pi r, and A of gamma vector for the circle of this one of radius r is pi r squared. And we can see that 1 by 4 pi into L of gamma vector squared is equal to 1 by 4 pi into 2 pi r whole squared, and this is given by 4 pi square r squared by 4 pi. And this we have pi r squared, which is equal to area bound by the interior, or bound by the simple closed curve, right? And let's have one proposition. This proposition also called as Wettinger's inequality, and this is used to prove the isoperimetric inequality. Right? So this inequality says that let f be a mapping from 0 to pi to r, and it be a smooth function such that f of 0 is equal to f of pi is equal to 0. Then 0 to pi of df by dt whole squared dt is greater or equal to 0 to pi ft whole square dt. And the inequality, or sorry, and the equality, of course, holds if and only if f of t is equal to t sine t for all t is an element of 0, pi, where d is a constant, right? And the proof is, of course, in Presley. We are not going to do that due to the paucity of time that we have. And so please find this in Presley's. So this is proof. It's in proposition 3.2.3 of Presley's book. It's a very intuitive, very nicely done proof, but it's quite long and quite long. So yeah, that's if it, and it's very easy to understand. So I think that's how it can be done, right? And finally, the theorem that we are going to discuss today is what is called as the four vertex theorem. So before that, let's talk about what when is a simple closed curve vector is called convex if its interior int of gamma vector is convex. Right? And what does convex implies? So convexity so a convex set is a set where any 2 points in the set can be joined by a line segment, by a straight line segment, and or maybe let me rephrase it so that okay, let's just keep it as it is, where any 2 points in this can be joined by a straight line segment, which itself or which is itself contained entirely in the set. Let's draw some figures to properly understand this. So say we have this set here, or maybe this simple closed curve gamma vector. Now, taking any 2 points within it, any 2 points, this or this, we can always connect this as well as this. You can always connect any 2 points by straight line, and all the points on the straight line are also in the set. So that is what it is. So this is a convex set. Right? And this is convex. And however, this is not convex. Let's find out the reason why. So we have these 2 points we can connect by straight line. This 2 as well we can connect by straight line. This and this we can connect by straight line. This and this. When we connect by straight line, this portion of straight line is not contained in the set. So S, right, let's call it S. And this also S, right? So it's not contained in the set. Maybe we don't even need to do that. Let's call as interior of gamma vector. And here, so it's not contained in the set interior of gamma vector. So this is not convex. Right? And let's have a definition. So a vertex of a curve gamma vector is T in R2 is a point where its signed curvature kappa of S has a stationary point. And the stationary point is d kappa S of dt by with respect to dt with respect to t is 0. So vertex of a curve is a point where its signed curvature has a stationary point, which means the curvature, the signed curvature doesn't change with respect to right with does not change with respect to those points, whether the signed curvature does not change with the parameter t. So say for example we have say if kappa of S, just as an example, right? If kappa of S, kappa S, which is the signed curvature, is say it has some say function. Maybe it varies with t as t. Okay? So when we take and we'll just find out in some time that we can construct any curve for which there is a signed curvature, and then using it we can construct the curve, right? So let's start with say if the curvature is t, then d kappa S by dt is equal to 1, which is never 0 for all t, right? Likewise, if kappa f is equal to t squared, then what we have is this is equal to 2t, but it can be 0. So now this is equal to 0 if t is equal to 0, right? So if say t is is element from say -1 to 1, if this is the parameter values the parameter t can take, then in that case we have one stationary point at t is equal to 0. And likewise, if say k of t is equal to t square minus t, then d kappa of S by dt kappa s is equal to 2t minus 1, and d is equal to 0 at t is equal to half. So this is our stationary point. And say in a special case of a circle, right? So for a circle, the sine curvature is kappa and it's a constant. In this case, d kappa s by dt is equal to 0. So which means every point in circle is every point on a circle is a stationary point. Right? So, and then this is invariant with respect to whatever we are talking about, whatever, right, whatever conditions we take, right? With whatever parameterization we take, be it unit speed curve or non-unit speed curve. Right? Okay, so an example goes here as, so let's take an example. And that too, consider the sine curvature of the ellipse, which is given by gamma t vector is equal to p cosine t q sine t, where p and q, p is greater than 0, q is equal to 0, greater than 0, and it is given by kappa of s t, and this can also be determined by gamma double dot or gamma dot t cross gamma double dot t dot k vector, which is just the normal to the plane or along the z-axis, divided by norm of gamma dot t cubed. Right? This was the expression for the curvature. And using this, we can obtain the expression of this one as pq by p squared sine squared t plus q squared cosine square of t to the power 3 by 2. Then d kappa of s by dt is equal to 3pq q square minus p squared sine t cosine t divided by p square sine square t plus q square cosine square t to the power 5 by 2. And this is equal to 0 at sine t cosine t is equal to 0, which implies that either t is equal to 0 pi and when cosine t is equal to 0, which happens at pi by 2, 3 pi by 2, when for t elements to 2 pi, right, for this range. So which means that, and the points corresponding to this are the, so the stationary points are the ends of the two axes of the ellipse. So that's what it is, right? So which means that this implies to say that and I mean in this theorem, let's write the theorem itself. So theorem, it's also called as the the four vertex theorem. I hope that's what I have written here. Yeah. So four vertex theorem. It states that every convex simple convex simple closed curve, sorry, in R2 has at least four vertices. And that is valid in the and four vertices implies that it's an ellipse. That's case for an ellipse. And the proof is again in this the book by Presley, and we are not going to discuss as of now due to the shortage of time. And of course, I would be very happy to discuss if you have any thoughts to follow through the proof. So with this, maybe what I'll do is I'll start with Mathematica. So let me share the screen.